Okay, so we have this equation. We get its characteristic equation, solve the characteristic equation, we get a solution. But the solution to the characteristic equation is repeated, so we don't get two solutions. Now we know since this is a second order equation, that we have to have two solutions to get a complete solution set, two linearly independent solutions. Okay, now we haven't proven that this is linearly independent, or that its Wronskian is non-zero. I'll probably go ahead and do that real quick. Because we haven't done that many Wronskians, but I could just also tell you what I told you here. Check the solution. Okay, so anyhow, to get a fundamental set, we require two solutions. Now I'm just telling you, for a constant coefficient equation, second order equation, if you get a repeated root, the other solution, you just throw a t in. Okay? And it works. Okay? But right now, you only know that it works because I told you to check it out and it works. Okay? You don't know where that comes from. You don't know how you would go about deriving this. Okay, well there's a technique for that, but right now let's just get the complete picture for second order equations, because you know what to do if you get two real solutions, and you know what to do if you get two complex or imaginary solutions. At least I hope you do. I think you do. And if you don't, just a quick review will remind you, okay? It's been a few weeks since we really talked about these. Of course, you're supposed to be working on them. Right? I know you. Smile. You know you're guilty. Fortunately, you're smart. You'll be able to do it. All you got to do is find the time. Okay, so your other solution is this. There's your fundamental set. What's a fundamental set? It's a set of linearly independent solutions in the space of functions. Okay? And you check its linear independence by doing the Wronskian. Okay? What's the Wronskian? Well, it's the determinant and you can work that out. Okay? If it's non-zero, the set's linearly independent. And in that case, the solution set spans the space of solutions. Okay? Because your solution set has a number of solutions that's equal to the degree of the equation. And you have to sort all that out, but read it. It's not hard to understand. Okay, maybe a little hard to prove, but not hard to understand. And this means that any solution is of the form this, okay? And anything of this form is a solution, okay? So I didn't have room to write that out. So I'll say it's a solution if and only if of this form. Now it means that if it's a solution, it's of this form, and it's of this form, it's a solution. So every solution has to have this form. Anything of this form is a solution, where A and B, of course, are implicitly constants.